Alright, hello class. We're going to now cover the last part of Chapter 1, the Introduction to the Chemistry of Life, and we're going to talk about thermodynamics. Thermodynamics is the study of the heat and the energy of a reaction. So we'll start with the first law of thermodynamics, which states that energy cannot be created or destroyed. So what does this mean? This means that heat and work can go in or out of a system, but the total energy of the universe does not change. So, for example, heat that's lost by an organism can be absorbed by the surroundings. Or work that's done by an organism to, for example, move an object is going to increase the kinetic or potential energy of the object. So these are two examples of energy getting moved around between different systems. But ultimately, on the whole, the universe contains the same amount of energy. When we talk about the heat of a reaction, when that's at constant pressure, that's referred to as the change in enthalpy for that reaction. So an exothermic reaction means that heat is absorbed, and there's a positive delta H. An exothermic reaction means that heat is released, and that's going to have a negative delta H. Now we're ready to talk about the second law of thermodynamics, which says that spontaneous reactions will increase the entropy of the universe. So there's a couple terms here that we need to discuss further. The first is spontaneous. What does spontaneous mean when you're talking about a reaction? A spontaneous reaction is a reaction that occurs without the input of energy. In other words, the reaction will go all by itself. You don't have to do anything to make that reaction happen. But this doesn't tell you the rate of the reaction. It might go very quickly, less than a second, a minute, an hour. It might go very slowly, years, eons, you don't know. You just know that it's spontaneous. It'll happen eventually. For example, one reaction that we know is spontaneous is the conversion of diamonds to graphite. However, this reaction is extremely, extremely slow, even though it is spontaneous. So now we have to talk about the entropy of the universe. So what is entropy? Entropy is a measure of disorder or randomness. So how do we know if the entropy of the universe is going to increase? It can happen in two different ways. The first is if the entropy of the system increases, and that's delta S, S meaning entropy, if delta S is positive, or if a reaction is exothermic, meaning delta H is negative, and this will therefore increase the entropy of the surroundings. So those are the two ways that the entropy of the universe will increase. And that brings us to talking about Gibbs free energy. The Gibbs-Helmholtz equation is going to tell us whether the entropy of the universe is increasing, and we can figure this out using only the information about the reaction that's occurring. So this is the Gibbs-Helmholtz equation, where delta G refers to the Gibbs free energy change, delta H, as we discussed, refers to the change in enthalpy, T is the temperature in Kelvin, and delta S is the change in entropy, as we discussed. So we know if a reaction is spontaneous if delta G is negative. To build off of that, we can talk now about delta G naught, and naught refers to this little symbol here. Delta G naught is related to the equilibrium constant for a reaction. And this naught means the reaction is happening under standard conditions. What are those standard conditions? We're at 298.15 Kelvin, we're at 1 atmosphere, and every component is at the concentration of 1 molar, the products and the reactants. This can sometimes be difficult when we're talking about reactions happening in biological conditions, because a lot of biological reactions involve protons, and if you have a whole lot of protons, a molar concentration of protons, you'd have a very low pH, which is not biologically relevant. So a further stipulation that we sometimes add is having a pH of 7. And then we can have a different energy constant that's known as delta G naught prime, where this is the prime symbol. So the equation for delta G naught is minus RT times the natural log of K, where R is 8.314 joules per mole Kelvin, and K over here is the equilibrium constant, which is unitless. It's the concentration of the products divided by the concentration of the reactants at equilibrium. So delta G depends on several factors, as we have discussed from the formula, and some of those factors include temperature, as well as the concentrations of the different components of the reactions. How can we calculate delta G? Delta G equals the delta G naught plus RT times the natural log of Q, where Q is the concentration of the products divided by the concentration of the reactants at any given point in the reaction. So if we want to know if the reaction is spontaneous at any point, we can use this equation. So why are we talking about thermodynamics in this biochemistry class? We know that living systems will never reach equilibrium because there's always energy being lost to the surroundings if you're alive. So delta G is always going to be less than 0. But living systems do exist in a steady state, so perturbations are quickly corrected. If something's too high, it's brought down. If something's too low, it's brought up. So chemical reactions are constantly need to happen to keep living systems happy. And so we want to know, and we can do this using thermodynamics, we can predict spontaneous biological reactions based on the concentrations of the reactants that are present, as well as the environmental conditions. A lot of biological reactions are spontaneous, but they don't always occur quickly. So as we discussed before, just because a reaction is spontaneous, it doesn't mean it happens fast. And a lot of times when cells need to make a change, to make that correction to a perturbation, it needs to happen fast. So that's where enzymes come in, which we'll talk a lot about in this course. Enzymes are catalysts that help a spontaneous reaction go more quickly by increasing the rate of the reaction. So now you're ready to answer the Chapter 1 Thermochemistry practice question.